चलिए आज हम लोग श्रोडिंगर वेव इक्वेशन फॉर पार्टिकल वेव्स को हम लोग सीखेंगे कैसे हमको मिलता है। ठीक है, तो श्रोडिंगर वेव इक्वेशन एक्चुअली डिराइव करना पॉसिबल नहीं है, लेकिन मैंने यहाँ पे आपको जो इक्वेशन यहाँ पे शो करके दिखाऊंगा उसमें मैंने जो कंसिडरेशन दिया है वो भी मतलब वैलिड ही लगता है। तो आप लोग इसको देखिए कैसे आया। तो श्रोडिंगर इक्वेशन जो है वो तीन कंसिडरेशन पे बेस्ड होता है। पहला, classical plane wave as we consider in the case of light and sound. Okay, so waves like this one, this is the y-axis, this is the position, and another is the de Broglie hypothesis. You already know this is the relation of the wavelength and the motion of the particle, lambda equal to h upon m into v. And the third one is the conservation of energy, as we know that the total energy is the sum of the kinetic energy plus potential energy. So we will derive Schrödinger equation using these three considerations. So let us first take the wave equation for a particle, that is the classical wave equation. You already used this equation in the case of light and waves, light and sound. Okay. So first we consider wave equation psi equal to a sin 2 pi x by lambda, where lambda is the wavelength, x is the position, that is the amplitude, that is a wave function. You already know about this. Okay. So first we differentiate this equation with respect to x. Okay. What you get, the differentiation of sign is the cos, and you see here this is the to further derive derivative of this 2 pi x by lambda, where x derivative will be 1, and we will multiply up the 2 pi by lambda. So we further differentiate this first derivative with respect to x. We get the second derivative, and then cos, the differentiation of cos is the minus sign, and 2 pi by lambda is further multiplied, so this becomes square. So if you simplify this one, you get del 2 psi upon del x square equal to minus 4 pi square upon lambda a sin 2 pi x upon lambda. Okay, and you see here a sin 2 pi x by lambda is equal to as same as equation 1. We can write this equal to psi. So this equation is very simple. You already did in the case of light and sound. Okay. So now we, as we know that the particle as a wave nature is more dominant for a microscopic particle, so we consider the de Broglie hypothesis, lambda equal to h upon m into v. So we put this value in equation second. So here I put here, then we square this one and we get the equation del 2 psi upon del x square minus 4 pi square m square v square upon h square psi. Okay. Now you see here, we know that kinetic energy equal to half m into v square. So from here m into v square equal to 2 into kinetic energy. So we can just this m into v square written as m into mv square. So we put mv square equal to 2k and 1 m is here. So now this equation is becomes as this. Now we also know that the total energy is the sum of the kinetic energy. So from here, what is the kinetic energy? That is the E minus V. So we put in place of K, E minus V, and the rest term is the same. So now we can transfer this equation, this right hand term in the left hand term. So this will become positive, and we get this equation. So this is the Schrödinger wave equation in 1D, because we have considered the one-dimensional motion of the particles. Okay. So this is the 1D equation for the Schrödinger wave equation. In case of 3D, we will consider three different coordinates. In that case, we have used the term del operator. Okay. So similarly, we can obtain the 3D. So we get del 2 psi upon del x square plus del 2 psi upon del y square plus del 2 psi upon del x square plus 8 pi square upon 8 pi square upon h square e minus b psi equal to 0. So this is the called as a Schrödinger wave equation for 3D. Okay, in three Cartesian coordinate. Okay, this is the Cartesian coordinate of the Schrödinger wave equation. So you get this equation by three consideration. So this is the simplification, development of the Schrödinger equation using this three consideration. Okay, so you practice it, and this is very simple. So next video I will show you how this equation can be written in the different form. Okay, Hamiltonian operator form, and in the another form and what is and how we can use this in the operator form. Okay. So if you like this video, then